Okay, in this lesson, we're going to talk about how to report your results for the results section. So this particular slideshow was adapted from a material that I usually send out to my students, Professor Guadano at the University of Nevada. She put this together, and rather than reinventing the wheel, I figured I would turn it into a PowerPoint and explain it. Now, what I will tell you is that in the APA manual, the 7th edition, there are many more examples on how to do this. This is just a primer, so it does not replace your responsibility for going back to the APA manual and checking up more information. So let's start with a little bit of background information. The results section, the general goal is to report the results of your data analyses that you use to test your hypotheses. So here's where you get to answer the research questions you had in the introduction. So you're going to need to identify the most appropriate statistical test, and you're going to have to report that statistic and provide some sense of interpretation of these results. Every analysis you run should be somehow linked back to your hypothesis. And if you're doing an exploratory hypothesis, you need to tell the reader that. And I think for a couple of you, when I sat with you with your results, I actually talked to you about doing other analyses beyond your research questions. But it's very important to tell the reader that you're doing an exploratory analysis so that they know that this is what you're doing. Otherwise, there is a big problem with something called p-hacking, where people collect massive amounts of data and they run a whole bunch of analyses just to see what came back to be statistically significant. When you do that, you increase the likelihood of finding a significant result in error or a type 1 error. So you want to avoid that if you can. Now, if your results are complicated or you have many conditions or dependent variables, it might be useful to have a model. A table or figure could be helpful. And as I said, you can see the APA publication manual for examples of different theoretical models and whatnot. Now, whenever reporting a statistical test, you have to report the descriptive statistics. Examples of descriptive statistics are means and standard deviation. If you have interval or ratio data, if you have nominal or ordinal data, frequency and percents. But inferential statistics, you're going to always want to report the degrees of freedom, the obtained test value, and the probability of getting that outcome, also known as the p-value. Now, in SPSS, they don't write the word p-value, they write sig, S-I-G, which is another way of saying the p-value. Now, when you have test statistics and p-values, they should be rounded to 2 decimal places. And if you're doing a meta-analysis and you are seeking more precision, then maybe 3 decimal places, but you should not allow the decimal places to go on and on and on. One thing that I will say that's important is that if you're using 2 decimal places, use 2 decimal places. If you're using 3 decimal places, use 3 decimal places, but be consistent. Don't in some places use 2 decimal places and in others use 3 decimal places. Now, all statistical characters are italicized. Now, it's interesting to note when we say statistical characters, there is a difference between a parameter and a statistic. A statistic comes from a sample, and they're written in regular English alphabet, or what we call the Arabic alphabet, and they're italicized. So the M for mean is italicized. SD for standard deviation is italicized. The T for the T value is italicized. The P for the P value is italicized, and so forth. So when you report statistical significance between two conditions, you want to indicate the direction of the difference. Was one condition greater than the other, lesser than the other, more or less, and so forth? And be aware that your audience tends to be either professionals or students who are trying to become professionals. So there's some level of knowledge of statistics. The average reader for a journal is more often than not a professor themselves. So when they read a journal, they have some level of knowledge of statistics. So you don't need to explain what the statistical test does, because that's just fluff in the eyes of the reviewers. So let's start with reporting p-values. Again, a p-value is the actual likelihood of getting this result by chance. And in general, there are two ways to report p-values. If you want to use your alpha, now we establish an amount of error we're willing to allow at the beginning. And standard science, the alpha for rejecting the null hypothesis is 0.05, and in some cases 0.01. So you could report your p-value in the first case, p is less than 0.01. So if you see the f1 comma 24 equals 44.4, that's reporting an f value. And then p is less than 0.01. That's one way to write p-values. Now you may also report p-values in an exact fashion. So p equals, right? So you can report your p-value as p equals 0.03. Now, when you do that, you're telling the exact probability that this occurred by chance. 0.03 is 3%. Now, when you have a p-value that is less than 0.001, it's sufficient to just write p is less than 0.001. Now, in SPSS, you'll know p is less than 0.001 because sig will be 0.000. Now, when it says sig is 0.000 in SPSS, that's not the real likelihood of that occurring. That is just saying that the likelihood of that occurring is less than 0.001. So you would write, as we see at the bottom of the slide, p is less than 0.001. So another thing to consider, and by the way, actually, let me go back a second. My preference for when you write your p-value is to write exact p-values. So the second scenario of p equals 0.03 is more consistent with what I am looking for in this class. Now, what about reporting non-significant results? Now, this is an example where various disciplines differ. And in social psychology, it's considered acceptable. Now, I happen to be trained from a statistician who said it's either statistically significant or non-significant. And some of the things I'm teaching you now would not fly in his class. But anyway, so there's a term marginally significant. So if your p-value is 0.10 or less, but not yet statistically significant, you can say your results were marginally significant. So an example, here's a write-up, and I realize I messed an italics up, but I'll correct that when we read it. Results indicate a marginally significant preference for pecan pie with a mean of 3.45 and a standard deviation of 1.11 over cherry pie, a mean of 3.00 and a standard deviation of 0.80. That standard deviation should be italicized with a t of 5 equals 1.25 and a p-value of 0.08. P equals 0.08, well, that's in between 0.05 and 0.10. So that phrase of marginally significant might fly in some social psychology journals. If your p-value is greater than 0.10, you could say your results revealed a non-significant trend in the predicted direction. So if you expected that there would be a preference for pecan pie over cherry pie, you can say that that was the anticipated direction, that was your hypothesis, but it was non-significant, p equals 0.26. Now, when reporting descriptive statistics, I said the most common ones are going to be means and standard deviation. So when we say a sentence like, and this might be in the participant section of your method, the sample as a whole was relatively young with a mean age m equals 19.22 and a standard deviation equals 3.45, right? That is one way to write it. There's another way to write it, which says the average age of the students was 19.22 years, open parenthesis, standard deviation equals 3.45. My preference is the first bullet point. Now, there are two ways to write it, but the first one is more appropriate for my class. Now, percentages are reported in whole numbers with no decimal places. So you might say nearly half of the sample was female, open parenthesis 49%, right? So as you see there. Now, so those are your descriptive statistics: percentages, means, and standard deviations. You might also report the range. That's another descriptive statistics. So you might say participants range between 18 to 25 with the mean age of 20 point blah, 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 right? Things like that would be giving greater context to the spread of age. Now let's talk about inferential statistics. When reporting t-tests, you may recall we use a t-test when you have two groups that you're comparing and the dependent variable is interval or ratio scale. Now, it's important to also know that there are different kinds of t-tests, right? So we know there are different kinds of t-tests. There are, in fact, 3 different kinds of t-tests. But the descriptive statistics for a t-test, you're going to report any variation that was employed. If you're using a one-tailed test, tell the reader that you're using a one-tailed test because we generally assume a two-tailed test. So here, again, there are 3 different t-tests. There's an independent samples t-test, a one-sample t-test, and a repeated measures t-test. And each one has different assumptions, but the reader generally knows what these assumptions are. But here are several examples on how you would report t-tests. There was a significant effect of gender, T, open parenthesis 54, that 54 are your degrees of freedom. T equals 5.43 with the p-value, p is less than 0.001, with men receiving higher scores than women, right? So if you write it that way, we know that whatever we're testing, there were significant differences between males and females. This sentence likely would follow a sentence before it that reported means and standard deviations. Now, the second example is the most preferred example for me. If you, results indicate a significant preference for pecan pie, mean equals 3.45, standard deviation equals 1.01, over cherry pie, mean equals 3.00, standard deviation equals 0.80. Your t-value with 15 degrees of freedom equals 4.00, and p equals 0.001. That is in my class, the preferred way to write your results. Now, I showed you the first example because you might see it in journals written that way. I showed you the second one to give you an idea of what I'm looking for. And then here is another example, also not necessarily what I'm looking for, but you might see in the research. The 36 study participants had a mean age of 27.4 with a standard deviation equals 12.6, were significantly older than university norm, 12.2, t-value is 35, t with 35 degrees of freedom, better yet, is 2.95, and p equals 0.01. So notice, you're always reporting means and standard deviations, you're always reporting t-values, degrees of freedom, and p-values. So that's how you report it. Now, it's interesting on this slide, the first bullet point would be a good example of an independent samples t-test. The second example is a good example of a repeated measures t-test. And a third example is a one sample t-test. Let me explain. In the first example, gender was categorized as a dichotomous variable. Even though we know gender, there are more than two genders, male and female. We know that, but in this particular study that was demonstrating this, they were comparing males to females. So you were either put in one category or the other. You were put in the category of being male, or you were put in the category of being female. And each group was independent of one another. So that's what we mean by an independent samples t-test. You're in one group or the other. A repeated measures t-test, you serve as your own control. So in this particular case, you might have given people the opportunity to taste pecan pie, and given people the opportunity, the same people, the opportunity to taste cherry pie and rate their level of quality. And so you go from a 1 to 5, and the average for pecan pie was higher on average than the cherry pie in this particular sample. So the participants ate both pecan pie and cherry pie. So that's what we mean a repeated measures t-test. They're comparing themselves relative to themselves. Then we have a one sample t-test. A one sample t-test is we're comparing our sample relative to the population as a whole. So that third example, we're comparing a sample of 36 participants, and we're comparing them to the university norm or university average of 21.2. So we know the population mean, we know the sample mean, and we're comparing this one sample relative to the population as a whole. Other examples include students taking statistics course in the psychology major at the University of Washington reported studying more hours for tests than did University of Washington college students in general. So now we're comparing psychology students relative to the general student body. I want you to think about what kind of test that is. And in class, I will ask you which of the 3 versions of t-test that was. The 25 participants had an average difference from pre-test to post-test anxiety scores of minus 4.8 with a standard deviation of 5.5, indicating that anxiety treatment resulted in a significant decrease in anxiety. T with 24 degrees of freedom equals minus 4.36, a p-value of 0.005. Notice you put here, if you're doing a one-tailed test, in parenthesis, you write one-tailed, because otherwise they're going to assume it's two-tailed, because that's the general assumption. Now, why might this particular study be useful as a one-tailed test? The answer is that if you're doing some form of treatment, you're hoping that the anxiety treatment has a specific effect, that is to decrease anxiety. If the anxiety treatment actually increased anxiety, that would not be a good thing. So you only want the treatment to decrease anxiety, hence one-tailed. It's a directional test. That's what one-tailed means, and you want it to occur in that way. Now, another example, the 36 participants in a treatment group, mean equals 14.8, standard deviation equals 2, and the 25 participants in a control group, mean equals 16.6 and standard deviation equals 2.5, demonstrate a significant difference in performance. T, 59 degrees of freedom, equals negative 3.12 with a p-value equal to 0.01. Now that's interesting. The degrees of freedom up to this point were put in parentheses with soft brackets. Now the question is, why do we have hard brackets here? And the answer is it's already in parentheses. So you have to distinguish the general parenthesis from the degrees of freedom parenthesis. So it's now written as a hard bracket. All right, so these are many different permutations on how to write t-tests. My preference, as I said, and I'm going to go back a slide, would be the second bullet point where it says results indicate a significant preference for blank over blank, t-value, degrees of freedom, p-value. All right. Some more examples. University of Washington students taking statistics courses in psychology had higher IQ than taking statistics courses in statistics. That's interesting. So if there might be a statistics major at the University of Washington and you compare them to psychology major, and now we're looking at the means of each of their IQ. And it's written very similar to the PCAM-PI, you'll notice. Mean and standard deviation, mean and standard deviation, T with 44 degrees of freedom equals 1.23, and the p-value equals 0.09. Now, what's interesting about this is 0.09. And we said that 0.09 technically is higher than the alpha of 0.05. So it would be, they had higher IQs, but for my class, I would say non-significant. I would write it differently. University of Washington students taking statistic courses in psychology had non-significant increases in IQ relative to those taking statistics courses in a statistics major, right? So that's how I would write it. But if you allow for what I said previously, marginal significance or trending towards significance, then this result would be phrased that way. Over a 2-year period, a 2-day period, participants drank significantly fewer drinks in the experimental group than those in the waitlist group. Again, another example of how I would prefer you to write it, with means and standard deviations, T degrees of freedom, and so forth. Now, the next thing we're going to do is talk about reporting ANOVA. ANOVA stands for analysis of variance, and we use an ANOVA when you have 3 or more groups and you want to compare them, and the dependent variable is interval or ratio data. Now, when you have 3 or more groups, it's not enough to run a regular test. You also have to run what's called a post hoc test, because if you have 3 groups and the general model is statistically significant, you may not know which group differs significantly from another. So the post hoc test, and there are tons of them, there are about 20 of them, would allow you to be able to determine where the statistical significance lies. Now, what do you report, right? So you report 2 forms of degrees of freedom. So you report the between groups degrees of freedom, followed by the within groups degrees of freedom, and they're separated by a comma. After you report the F statistic, you do F equals, you put the significance level or the p-value at the end. So here's an example of reporting one-way ANOVA results. The 12 participants in the high dosage group had an average reaction time of 12.3 seconds with a standard deviation of 4.1. The 9 participants in the moderate group, dosage group, had a reaction time of 7.4 seconds with the standard deviation of 2.3. And the 8 participants in the control group had a mean of 6.6 with a standard deviation of 3.1. Now I'm going to stop there for a second and highlight you have 3 groups, right? The one-way ANOVA is used for 3 or more conditions. So you have the high dosage group, moderate dosage group, and the control group. And now you look to see if there were significant differences. The F with 2 degrees of freedom between groups and 26 degrees of freedom within groups equals 8.76 and a p-value of 0.012. So that effect was statistically significant, right? Because it's equal to or less than 0.05. Okay. So now here's another way of writing it. And this is actually my preferred way. So a one-way analysis of variance showed that the effect of noise was significant. F with 3 degrees of freedom between groups, 27 degrees of freedom within group equals 5.94 and a p-value of 0.007. Now, so that's the general model. We have significant differences across noise. Now, which groups differed from one another? We don't know yet, right? So we have to do a post hoc analysis. So here's how you would write the results of a post hoc analysis. Now, the post hoc analysis, you report significant differences between the groups, and that's it. So post hoc analysis using Sheffi post hoc criterion for significance indicated that the average number of errors was significantly lower in the white noise condition than the other 2 noise conditions. Notice how you put the means and standard deviations for all of them, and then the p-value. So that now we know that if you had a difference between traffic-based noise, industrial noise, or white noise would be the preferred noise because it's going to result in the fewest number of errors. All right. There's another form of a post hoc test, which is a Bonferroni, which adjusts the alpha based on the number of conditions. So here's an example how you would write this. Tests of the 4 a priori hypotheses were conducted using a Bonferroni adjusted alpha levels of 0.0125 per test. And how did they get that? There were 4 tests, right? So they did 0.05 divided by 4. The results indicated that the average number of errors was significantly lower in the silence condition than those in both the white noise condition and the industrial noise condition. And then obviously you report the F values and means and standard deviations. The pairwise comparison of traffic noise condition with the silence condition was non-significant. And in this case, the author chose to report non-significant differences, but I don't require you to do that. All right. There was a significant, so now we've talked about one-way ANOVA. A one-way ANOVA occurs when you have 3 or more conditions. Your dependent variable is interval or ratio, but you're dealing with one independent variable. There's also something called a factorial ANOVA. Now, a factorial ANOVA requires you to have 2 or more independent variables. Now, what can you find different from a factorial ANOVA relative to a one-way ANOVA? Well, one-way ANOVA looks at the impact of a single independent variable, whereas a factorial ANOVA looks at the impact of a single independent variable, but it also looks at the interaction between multiple variables. So the main effect would be the general effect of a single independent variable. An interaction effect would say that variable A and its relative impact depends on the conditions of variable B. That's what an interaction is. So let me show you how to write factorial ANOVAs. There was a significant main effect for treatment. F1 between group degrees of freedom, 145 within group degrees of freedom, with F value of 5.43, a P being less than 0.01. And so there was a significant main effect of treatment and a significant interaction. Then you report the interaction. F2, that's between groups, with 145 within groups degrees of freedom is 3.13 and P is less than 0.05. So that would be the generic way to write that you had a main effect and you had a significant interaction. Now it's possible that you didn't have a significant main effect for one independent variable, but you had a significant main effect for another. It's also possible that you had no significant main effects, but just a significant interaction. Any number of these can occur. Now, the cell sizes, means, and standard deviation can be found in a table. You tell the reader, right? So you put a table showing all of this information. That's another way to do it, so you don't have to splatter a whole bunch of numbers on the page. The main effect for dosage was marginally significant. There goes that buzzword. F2 between groups, 17 within groups, a p-value of 0.067, right? As was the main effect for dose category, also marginally significant. What's interesting, when I write this, I would report that as non-significant because of the way I was trained. Now, the interaction of dosage and diagnosis category was significant. Look at this p-value. P equals 0.0005. Now you could write that as P is less than 0.001. But here are just examples of how you write these things. There are other examples, again, fully fleshed out, teaching you how to write the full paragraph. So this model right here is a very good example of how you would write a factorial ANOVA in a paragraph form. Attitude change scores were subjected to a two-way analysis of variances, having two levels of message discrepancy, small or large, and two levels of source expertise, high and low. All main effects were statistically significant at the 0.05 significance level, right? So that's generic. And so now you know they're going to do greater than, less than it, rather than their specific p-values, right? The main effect of message discrepancy yielded an F value of 44.4 with the p-value being less than 0.001, indicating the mean change score was significantly greater for large discrepancy messages, mean and standard deviation, than small discrepancy messages, mean and standard deviation. Notice how they report the model. Notice how they report the means and standard deviation for each group. So the general model was significant. There was also a main effect of source expertise yielded an F value of 124 equals 25.4. So that F value is 25.4 with the p-value being less than 0.01, indicating that the mean change score was significantly higher for higher expertise messaging source than low expertise messaging source. The interaction was non-significant. F 124 equals 1.22 with P being greater than 0.05. Be careful with your greater than, less than. You may remember the symbol greater than, it faces the greater than is where the opening faces. So P is greater than 0.05. All right. Now, this would be, for my class, the most ideal way to report a factorial ANOVA. Another way to do it, a two-way analysis of variance yielded a main effect for the diner's gender, right? And then it reports the F value, the degrees of freedom, the actual F value itself, and it was less than 0.05, such that the average tip was significantly higher for men than women, and it reports the mean and standard deviation of tip. The main effect of touch was non-significant. Now, there's research that suggests that if a server puts their hand on your shoulder, it could create a connection between you and that person, increasing tips. There have been studies. In this particular study, it was non-significant with P being greater than 0.05. However, the interaction effect was significant, indicating that the gender effect was greater in the touch condition than non-touch condition. What are they saying? That males who were tapped on the shoulder tended to tip more than when they were not tapped on the shoulder. We already knew males tip higher, but even among males, it was significantly higher when they were touched on the shoulder than not. So that is a rundown of t-tests, one-way ANOVA, as well as factorial ANOVA. Moving forward, we're going to talk about things that look very similar to correlations. So Chi Sqaure correlation and regression analyses tend to look very similar as well. Now, a Chi Sqaure can be a one variable Chi Sqaure. It could be a two variable Chi Sqaure. So there can be multiple variables in Chi Sqaure. So a chi-square is typically done for nominal data. That is when we're looking at categorical differences. And the data is measured in frequency frequency or percent rather than means and standard deviations. So here would be how you would write different chi-squares. The percentage of participants that were married did not differ by gender, right? So this is a chi-square. X superscript 2 is a symbol for chi-square. Notice it's italicized with 1 degree of freedom and 90 participants was equal to 0.89 and the p-value was greater than 0.05. So another example, give me 1 second, would be to write the sample included 30 respondents who were never married, 54 who were married, 26 who reported being separated or divorced, and 16 who were widowed, right? So if you have 4 conditioned, the degrees of freedom for a chi-square is n minus 1, right? So you're going to have 3 degrees of freedom. If you add up the number of participants, you're going to have a total of 126 participants. That chi-square value was 10.1 with a p-value of 0.017. In this case, we would say the frequencies were significantly different. Notice how chi-square, you're emphasizing either frequencies or percents. Now, as can be seen in the frequencies cross-tabulated in table X, right? This is another way to write it. There is a significant relationship between marital status and depression. Get this, when you're using a 2-variable chi-square, you're looking for whether the factors are independent from one another or whether they're related. If you have statistically significant findings, those factors are related. So marital status and depression were related, right? So this one in particular had 3 degrees of freedom. So if we were to look at this, and we would have to do it as categories in this case, the marital status would be, there are 4 of them, right? Never married, married, divorced or separated, and widowed, right? In order to get the degrees of freedom for 2 factors, you multiply the degrees of freedom of one variable by the degrees of freedom of the second. So if there are 4 conditions, the degrees of freedom for marital status or relational status is 3, because 4 minus 1 is 3. And then depression, for it to be categorical, is did they have depression or not? Yes or no? Well, for the depression category, yes or no, there are 2 categories. 2 minus 1 is 1. So 3 times 1 equals 3. And that's how you got, in this particular scenario, 3 degrees of freedom. All right. And so there's a relationship between depression and marital status. P is greater than 0.001. And that actually is a true finding. Interesting to note, there's research to suggest that people who are married tend to be happier on average than their counterparts. So that's an interesting finding. Preference for the 3 sodas were not equally distributed in the population. So again, one of the assumptions of a chi-square is that you have equal number of frequencies across the groups. So if you find significant differences in the categories, we would say that they're not equally distributed. All right. Reporting correlation. Again, correlations are reported with degrees of freedom, which is n minus 2. So we're taking off the 2 variables that we're correlating in parentheses and the sig value. So here would be an example of writing the two variables were strongly correlated. R is the symbol for correlation, with 55 degrees of freedom. So you look at the total sample size and subtract 2 from it, right? So R with 55 degrees of freedom equals a correlation of 0.49, and P is less than 0.01. So that's significant, right? Now, when we talk about a correlation, we're talking about a bivariate correlation. Now, correlation, you could just look for relationships between variables as the previous slide did, or you can use a more sophisticated form of correlation that's designed to predict an outcome. And we refer to this as a regression analysis. So regression analyses are best reported with tables, and the AP manual has a whole bunch of tables for regression analyses. But I will say that there's not a lot of structure around how people report regression analyses. However, at a minimum, you should present your standardized slope, which is your beta, which is symbolized by a lowercase b, along with the t-test and the corresponding significance level, right? So we want to see if the slope was significant, so that if the general trend or predictive value was significant. Now, how do we calculate degrees of freedom? So we calculate n minus k minus 1, where k equals a number of predictors. So k might refer to number of groups, but in this context, k is number of predictors. And it's customary to also report the percentage of variance explained by the corresponding f-test. So here would be how you would write a regression analysis, putting it all together. Social support significantly predicted depression scores. So if you had more support, you had lesser depression. And how do I know that? Because beta B equals minus 0.34. Well, that's a correlation. The slope, the trend is a negative correlation. So as one factor increases, the other factor decreases. So increased social support resulted in or predicted lower depression with a t-score value with 225 degrees of freedom equal to 6.53 and a p-value less than 0.01. Now, so social support. So now that we know that social support predicted depression, we want to know how much of depression was explained by social support alone. So for that, we use R square. So for R square, we would say social support also explained a significant proportion of the variance in depression. R square equals 0.12. F equals 1, comma 225, which the F value was 42.64, and P equals or was less than 0.01. So now, the only reason why we said social support explained a significant proportion of the variance is because the p-value was less than 0.05, right? All right. One last thing, because results, usually you also share tables. Now, I will tell you that there are rules about reporting tables. Only report tables that add value. If the table does not add any new information from the text, don't include it. But many results have tables. And here are the rules around tables. There are no vertical lines. Now, vertical lines go up and down. No vertical lines in your tables. There are no periods used after the table number or title. Again, the table number goes up top. Then you have the title of the table, then the table. And then when using the columns, make sure that the column numbers line up, right? And the points line up for visibility. Now, what I always tell people to do is right align it. Make sure you highlight the table and you right align it. And it's very easy to do in Microsoft Word. So with that, I will stop the lesson. And that is a very, very detailed yet basic guidance on reporting your statistics and writing up your results. So I'm going to stop there.